Okay, audio's working. Start signing in, please. Well, I want to direct everyone's attention to the board. See the big black date written up on the board? Anybody want to guess what that date is? That's the last day to turn in late work. Now, that's also the last day before spring break. Okay, so I figure if I have everybody turn in their homework, any late work by then, I'll have the whole week of spring break to get it graded. I also want to make something clear. You can still turn in late work after this date, but it'll only get graded if I have time. Okay? So anything that you turn in after this date may or may not. You may or may not get credit for it. Okay? You can turn it in, I will still accept it, and I will put it in a separate folder, and if I get a chance to grade it, I will grade it, and you'll get credit for it. And if I don't get a chance to grade it, no guarantees. So this is the last date that you can turn something in, and I will assure you that you will get credit for it. All right? That's the deadline date right there. Last day before spring break. I was just explaining to him, if you turn something in by then, late work, I will assure you that I'll get it graded over the spring break, and you'll get credit for it. If you turn something in after this date, I'll put it in a separate folder, and if I get a chance, I will get it graded, and you'll get credit for it. And if I don't get a chance, then you won't. But anything you turn in after this date is no guarantee. All right? Does everybody understand that? Oh, good night. Well, you're going to have to ask all your friends, because I'm not going to repeat it a third time. This is the date you want to remember. The last day before spring break. All right. So we are still talking about centripetal acceleration, centripetal forces. We talked about, last time we went over how Isaac Newton figured out about centripetal acceleration, centripetal forces, with his his thought experiment about throwing an apple all the way around the earth. And in that moment, he had the epiphany that there's a reason that everything in the celestial realm moves in circles, and it's because of centripetal acceleration. Things are floating around in space, and the only forces acting on them are centripetal accelerations, gravity from other objects pulling on them. So let's look at the actual kinematics of centripetal acceleration. When we have something moving in circular motion, it's moving in this direction, but the direction of its motion is constantly changing. So that as it moves to here, it's now pointing in this direction. Those are its velocity vectors. This, of course, is after some time delta t. And if after it moves some distance, delta theta, or it subtends some angle, delta theta. Well, obviously the force acting upon it is pulling it in, pointing towards the center, which is what centripetal means, literally means center pointing. And now from this we know that the definition of acceleration is the change in velocity divided by the change in time, by delta t. Or okay, well, let's look at what is delta V here. Well, what is V2 minus V1? Well, just without breaking it down into Cartesian and polar coordinates and doing all of the arithmetic, just let's look at the graphic method of looking at adding and subtracting vectors. If we added V1 and V2, it would result in that resultant vector. But subtraction is the addition of a negative. So if we want to subtract V1 or V2 from V1, what we do is we have to draw V2 and then add to it the negative of V1. Well, if this is V1, then negative V1 is simply this, pointing the other direction. So we add negative V1 to it, and we get this delta V. I actually drew it the wrong direction, but pointing in. Okay? That's our delta V. Well, you'll notice that as this velocity vector sweeps out this angle theta, it also forms a right triangle, and yes, it's a right triangle, just I don't have a square to draw it with. And in that time, it sweeps out this distance. It travels this distance, delta L, that arc length. Okay? Here's the important point. As long as we're talking about some finite period of time, this arc length delta L is not going to be exactly the same length as this opposite side of the right triangle. But they're going to be close, as long as you're talking about a very small angle. And so delta V also, when you look at these two angles, these two vectors, that angle is the same angle. You analyze it geometrically. And so you end up with these two similar triangles. They're similar as long as you're talking about this right triangle, not the whole area swept out by the arc length. Okay, so we have these two similar triangles. Where delta V divided by over the length V this triangle here is almost equal to delta L, that arc length, divided by R, by the radius. So we have this relationship. They're almost equal. Now, when we are looking at the velocity, the instantaneous velocity, we're talking about this relationship when delta t, in the limit that delta t approaches 0. As delta t gets smaller and smaller and smaller until it gets right up to 0, well, as that happens, then this angle, delta theta, gets smaller and smaller and smaller, and so does this arc length, delta L. So in the limit that delta t approaches 0, then that almost equal becomes an actual equal sign. In the limit that delta t approaches 0, this approximation actually becomes a literal equal, an exact equal sign. And that means we can now write the delta V is equal to V over R times delta L. Everybody with me so far? Well, that's our change in velocity. But our acceleration is change in velocity divided by time. So if we divide our change in velocity by the change in time, then that becomes V over R times delta L over delta T. But what is delta L over delta T in the limit that delta T goes to 0? That's just your velocity, change in position per change in time, meters per second. So since we're talking about in the limit as delta t goes to 0, then we can change this delta v per delta t, which is our acceleration, our centripetal acceleration. This delta L delta t becomes a v, and we end up with v squared over r. That is the centripetal acceleration. What have I assumed about this? Have I assumed any special condition? The only thing I've assumed is that the direction of this velocity vector is changing. Now that implies that the magnitude of this velocity vector is staying the same. And as long as the magnitude of the velocity vector does stay the same, then that acceleration will cause it to rotate in a perfect circle. And that's where we get the phrase uniform circular motion, when the velocity vector doesn't change. But this expression for centripetal acceleration is going to be true whether the velocity vector is changing or not. Now, the motion will no longer be in a circle, but this acceleration will still hold true during that period of time. And that's why you would call that, if you were analyzing something where it underwent a centripetal acceleration for a short time, you would talk about the radius of curvature for that one path, even though for that one short segment, even though there was no full circle involved. For now, let's keep talking about complete circles. So for now, we're going to restrict ourselves to uniform circular motion. And that means we're going to talk about how long it takes for the object to move around that full circle. How many of you are familiar with the unit hertz? Frequency equals cycles per second. How many times will it go in a full circle every second? Okay? Now, the reciprocal of frequency is how many seconds there are in each cycle. And that's the period. How long does it take the object to travel around? That's pretty obvious. If it's traveling in 2 cycles per second, then it takes 1/2 of a second to complete a full cycle. So, how far will an object travel in one complete cycle? What's the distance an object travels when it travels a full circle? What? 2 pi r. Is the distance that an object travels. If you divide that by the time it takes to travel it, you end up with its velocity. And here, if you're following along in the book on page 111, example 5.1, look at the acceleration of a revolving ball. It says a 150-gram ball at the end of a string is revolving uniformly in a horizontal circle of radius 0.6 meters. And the ball makes 2 revolutions every second. What is its centripetal acceleration? Well, what do we have? It makes 2 revolutions per second, so the period is 1/2 of a second. Its velocity then, its radius that it's moving in is equal to 0.6 meters. So its velocity is 2 pi times 0.6 divided by 1/2. Which is 4 pi times 0.6. Somebody want to break out a calculator and double check this with me? We've got 4 pi times 0.6. .54 meters per second. Okay, so now what then is what is the centripetal acceleration of this ball? V squared over R. .85 meters squared per second squared divided by 0.600 meters, which gives us .94 to 3 significant digits, 0.8 meters per second squared. Did you notice that at no time did we need the mass of the ball, even though they gave us the mass is, what, 1.2 grams or 150 grams? When would you need the mass? This is important. This is going to come up in the lab tomorrow. If you want to know the centripetal force, the centripetal force is equal to the mass times the centripetal acceleration. You'll notice they didn't ask what is the centripetal force, they asked what is the centripetal acceleration. Now, let's talk about some of the dynamics of centripetal or circular motion. Think about slinging a ball on a string. Let's take a minute and talk about this. There is a common misconception amongst people, and the people in general, that there is something called a centrifugal force. Centrifugal, which is the opposite of centripetal or centripetal. Why do people get this impression? Why do people think that there is such a thing as centrifugal force? It's all about perspective. You're riding in a car. The driver suddenly makes a hard left turn. You're in the back seat. What happens to you? You're not belted in. You slide out to the right-hand side of the car and get smashed up against the passenger door. You feel an outwardly directed force. Why? Same reason that cup of slushy doesn't stay on the dashboard when the driver guns the gas pedal at the red light as soon as it turns green. You have inertia. You may not feel like it when you're inside the car because you're in that inertial reference frame, and relative to the inside of the car, you're motionless. So you would expect to remain motionless. Intuitively, you would expect to remain motionless unless acted upon by an outside force. Well, when the car suddenly turns left, it is no longer an inertial reference frame. And you will no longer remain at rest in that reference frame. You have inertia too. You want to continue moving in a straight line, and you do exactly that until the door exerts an inward directed force on you. But from your perspective, you are pushing on the door because every force has an equal and opposite reaction, or an equal and opposite. So when the door is pushing you to the center of the radius of curvature, you are pushing out on the door with the same force. And that's why people get the idea that there's such a thing as centrifugal force, because that's what they feel when they experience it. But all they're actually experiencing is the law of inertia. The real forces involved are pointing in towards the center of the curve, because that's the direction you end up moving. You end up making that same curved motion that the car makes, and that's the acceleration that you feel. You just experience it as the normal force to the acceleration force. How many of you have ever watched, I asked a couple of y'all this before class. Who's the cowboy from Oklahoma that never met a man he didn't like? Is that Will Rogers? Good, got that right. Roy Rogers has Trigger. Will Rogers was friends with Wiley Post. They died in the plane crash together. Didn't Will Rogers used to do rope tricks where he'd sling that lasso in a big circle and make it jump up and down and jump through it as he would? Am I thinking of the right guy? No? Okay, well, never mind who it was. Have you ever seen anyone do rope tricks like that with a lasso? Have you ever noticed that when they do, the lasso is always going up and down? Even when they're spinning it in a horizontal circle, it's going up and down. It's not ever sitting in just one flat circle. How about if any of you have ever played with the yo-yo? Have you ever spun it around on a string? And have you noticed that when you spin it around in a vertical circle, that your hand doesn't stay in one spot, that your hand actually goes up and down with it? Let's look at why these things happen. First, let's imagine spinning a ball on the end of a string. Here's your mass. Here's a string. And that point is as close as I'm going to get to trying to draw a hand holding the string. Okay? Can you imagine spinning that ball in a perfectly flat horizontal circle? Fact is, if you really tried it, and I've got a brass ball on a string in there. I was thinking about trying this as a demonstration, and I decided I wasn't going to sling a solid brass ball in a circle and hope that it doesn't break or slip out of my fingers. But you can imagine doing this. And if you get it spinning fast enough, you could actually get it fast enough where it would look to you like it was in a flat circle. But in point of fact, it will never, ever be in a precisely flat circle. Think about do a free body motion here, free body diagram. What are the forces acting upon this ball? There is the centripetal force pulling it in at mass times v squared over r. But there is also this force, which is the mass times gravity, pulling it down. So the net force is always going to be the sum of it's going to be the sum of two forces. Now, if this were the actual diagram of the forces involved, then the net force would have to be this force pointing in this direction, which means your string would actually be at some upward angle theta. Of course, you're going to have to swing pretty hard to keep it up there, and that's why generally when they're doing that with the rope, they get it to spin up for a little bit, then it comes down, and you end up with the string tension pulling this direction, which gives you this component of the force of tension times the sine of theta equal to minus mass times gravity. And this horizontal component, which is equal to the force of tension times the cosine of that angle theta, which is then equal to the mass times the velocity squared over r, or the centripetal acceleration. Okay? The point is, you're never ever going to get the ball to spin in a perfectly flat circle. It will always deflect up or down some, because this force, mass times gravity, never goes away. It has to be counteracted. Now, in this case, you've got the tension pulling down, which is actually adding to mass times gravity. You notice this? You've got the tension pulling down, so you've got this force, this component of that force, which is actually adding to mass times gravity, making it even worse. What I was saying a while ago. It means that your downward force now is twice that. And that means that when you've got it spinning up above your head, there's no way to keep it there. What about if we spin that ball in a vertical circle? What are all the forces acting on it when it's here? There's the tension acting this way, and the normal force against the tension, but there's also mass times gravity pulling it down. When you get down here, you've got the tension pulling it up, but mass times gravity pulling against it. Okay? So here, the normal force is equal to the sum of the tension plus the force due to gravity. Here, the normal force, you have a net force that's equal to the difference of force of tension minus the force of gravity. Now, since the sum in order for it to form excuse me. In order to have circular motion, the sum of the forces have to equal the centripetal force. That has to be the net force pointing in that circle, causing the circular motion. What is the effect now going to be when you're up here? The net force has to be larger up top and smaller at the bottom. Well, what changes? What, other than the total force, the force is equal to mass times acceleration equals mass times velocity squared over r. Does the mass change? Mass does not change. Does the radius change? If the radius changes, it's not centripetal, it's no longer uniform circular motion. The only thing that can change is the velocity. Since the net force down here is less, the velocity at the bottom has to slow down. Force is greater at the top of the circle, so the velocity around the top of the circle has to get faster. Now think back to your days playing with yo-yos and spinning balls on strings, and I think you can imagine pretty quick, you can realize pretty quickly that when it's getting to the top, you're having to pull on it, so your hand ends up moving up and down as you sling it in the circle. Because if you'll think back, you'll realize it doesn't travel as fast at the bottom of the circle as it does going around the top. Now, have any questions so far? Questions, thoughts? What about from the homework? Anybody have any questions from your homework? Well. Let's start talking about cars and curves and banked highways and unbanked highways. How many of you watch NASCAR? Have you ever driven on a NASCAR track? What happens if you drive too slow around those curves, those banked curves? Huh? Oh, no, actually, you slow down too much around those banked curves and it gets very much the opposite of boring. He's right. If you're not going fast enough around those banked curves, you won't stay up. You'll slide right down and crash. Why is it bad when you start sliding and when you're driving and you start sliding? What is the one thing that we know about the different coefficients of friction? Static versus kinetic. We know that static friction is always greater than kinetic friction. That means when you start sliding, you lose static friction, and rolling friction is an application of static friction because the tire is not moving relative to the surface of the road. Once you break that static friction, once you exceed the force that it can withhold, suddenly you're in the realm of kinetic friction. And that's always less than static friction, which means your car starts moving in the wrong direction and there's absolutely nothing you can do to slow it down or stop it except wait for the kinetic friction to slow you down enough for the static friction to catch again. As once you start sliding, you can't stop sliding until you just stop. And then static friction can take hold again. Yeah. I know people like to look at these Fast and Furious movies of the cars drifting and stuff. And what they're doing is they're playing right on the critical edge of losing friction laterally and still holding on to it in the in a straight line. They're giving the illusion of maintaining control of something that they have no control over. Yeah. But in general, if you're in the parking lot doing donuts and you suddenly slide out of control, when do you regain control? After you come to a complete stop and hopefully haven't damaged your car. Now, let's look at, do they have an example here of a car on a flat surface? Talking about a 1,000-kilogram car rounds a curve on a flat road of radius 50 meters at a speed of 15 meters per second, or 54 kilometers per hour. Will the car follow the curve, or will it skid? Assume that the pavement is dry and the coefficient of static friction is 0.6. Then assume that the pavement is icy and the static coefficient is 0.25. Static coefficient? Wow. Just wow. The coefficient of static friction. All right. Well, it's a flat road. So, mass of gravity and the normal force are equal and opposite. They cancel out. There's no net vertical acceleration. And that's 1,000 grams times 9.8 meters per second squared. So that's 1,000 kilograms, right? Yeah, okay. 1,000 grams is not a very big car. That's more like a Hot Wheels. So we end up with 9,800 newtons. Look at that. Even I can do that multiplication. Now that means before we do the centripetal acceleration and forces, let's look at what is the maximum force due to friction that we can withstand on what's the maximum force of static friction we're going to get? 0.6 times 9,800. That's going to be our mu sub s times our normal force. And that equals, they did the arithmetic, right? Yeah, 5880. Newtons. So if our force due to centripetal acceleration ever exceeds 5,880 newtons, car is not going to make the curve. So what is the radial? It's going to be mass times the acceleration. Centripetal force is going to be the 1,000 kilograms times centripetal acceleration, which is v squared over r. So that's 1,000 times, what was our velocity? 15 meters per second. And the radius is 50 meters. So we got 15 squared divided by 50. And that I can't do in my head. Somebody with a calculator do it. Double check me here. Get 4,500 newtons. Is that what everybody gets? All right. So that tells us that this car will make that curve without sliding out of control. And of course, if it's on an icy road, well, then we just change 0.6 to, what did they say, 0.25, 9,800. And that would be 2,450 newtons, which is nowhere near what the centripetal force would be. So on ice, as you would expect, the car would slide off into the ditch, which apparently may happen to some of us this evening going home. All right. Everybody understand? Everybody see how this is done? How this kind of problem is solved? What if we wanted to know what's the maximum speed this car could take around that corner? Well, we know that the maximum force of static friction is going to be 5,880 newtons. So let's just set that equal to the centripetal force. To our 1,000 kilograms times v squared divided by 50 meters. Now, we divide both sides by 1,000 and multiply both sides by 50. And just for good measure, write it backwards because I'm apparently doing everything backwards today. And we end up with 50 divided by 1,000 times 5,880. And that's 294 is v squared, so v would then be 17.1 meters per second would be v max. What's that in terms of kilometers per hour? Go 61 points, multiply by 3,600 seconds per hour, and you get 61,700 meters, or 61.7 kilometers per hour. Have any questions on how this is done? Okay, just one quick reminder. 15th of March, that's the last day to turn in any late work and be guaranteed that I will get it graded over spring break and you will get credit for it. If you turn something in after the 15th of March, I will put it in a folder and I will try to grade it, and if I have a chance, I will grade it and you'll get credit for it, but if I don't have a chance, then it won't get graded and you won't get credit for it. Save on. See y'all tomorrow.